Hi Randy, this is Chris. I'm back again talking about chemistry for you. So before I get into balancing chemical equations and talking about stoichiometry, which is um, kind of a natural progression from your balancing, before I do that, I just want to talk a little bit more about some of the terminology that goes into chemical reactions. And you are familiar. At this point, you should be fairly familiar with the energy time diagram of a reaction. So here's energy, and here's time. All right. So I have energy over time, and if I just plot a spontaneous or an exothermic reaction, I'll have my reactants here. All right, and there'll be an activation energy barrier that I get over, and then I go down to my products here. All right, so this is a typical exothermic reaction, and we know that this is exothermic because I have a certain amount of energy here that's higher, and then I end up with a certain amount of energy here that's lower, and so we know in this case that energy must have been given off. Okay, that's really what an exothermic reaction is. This is nothing new. You know this. But now what I want to do is I want to talk a little bit about this energy, because this is a very important concept in chemistry and chemical reactions. So let me just cover what energy is just really quick, just a little bit of physics here. What is energy? Well, energy is simply what we call the ability to do work. Okay, the ability to do work. So I kind of think of energy as kind of like money. Okay, so you have money in the bank. All right, you have money in the bank, and then you spend that money. Okay, so energy is like the currency for work. All right, so you spend that money in the bank. You do work, and so work and energy, okay, are defined in the same units. So we use the same units to define work and energy, and the reason being is because all work is just the expenditure of energy, right? That's all work is. So when I do work, I'm expending energy. Now I can have energy. I can have all this energy built up and not necessarily expend it. So if I haven't expended it, I haven't done work, then I haven't used the energy. So really energy and work are in the same units. They just mean slightly different things. Okay, so let's just talk about what work is. Work is nothing more than a force. Okay, so I apply a force, and I apply that over a distance. So work literally equals force times distance. Okay, so let's break this down a little bit. Distance in chemistry and in international units, the fundamental unit of distance is the meter. Okay, and then force is, what does force do? Well, force causes acceleration, and I'm just going to put A with a line to let you know that that's a vector value. So the force causes acceleration, and the fundamental unit of force, okay, so the fundamental unit of force is what we call the Newton. Okay, the Newton is the fundamental unit of force. Okay, and a Newton, what a Newton is if I have a 1 kilogram object here. Okay, so let's say this object is 1 kilogram. Okay, and we'll just say that's at rest. Okay, it's not moving, and I apply a force of 1 Newton. Okay, and I apply it in this direction here. So I apply a force of 1 Newton. That will cause this 1 kilogram object to accelerate by 1 meter per second, or 1 meter per second squared, or 1 meter per second net minus 1. Okay, it'll accelerate. And an acceleration is just a change in the velocity, and the velocity is just the speed plus direction. So acceleration is changing the speed and direction. Okay, so that's what 1 Newton of force is. So let's just clear this. Okay, so going back to work equals force times distance. So distance is the meter, all right, and the fundamental unit of force is the Newton, all right, and so the fundamental unit of work is Newton times a meter, or the Newton meter, and 1 Newton meter of force is also known as a joule. Okay, or 1 Newton meter of work, rather, is known as a joule. So 1 joule is simply a force of 1 Newton applied over a distance of 1 meter. Okay, that's what 1 joule is. And joule is not only a measurement of work, but joule is also a measurement of energy. We measure energy in joules because energy is the currency we use to do work. Okay, cool. So now that we got that little bit of physics out of the way, the reason I wanted to let you know, because when we do chemical reactions, and I have energy over time, and I have, let's say, an exothermic reaction, and I'm giving off energy, I measure that energy in joules. All right, the energy released in joules. Okay, I can also have, we'll do that here in every time. I can also have an endothermic reaction, where I'm having to put energy into the reaction to make it go. That's also measured in joules. Okay. Occasionally, you may see people use the term calorie. Okay, a calorie, and 1 calorie is approximately equal to 4.18 joules. Okay, and you may even hear the term 1 kilocalorie. All right, which is just 1,000 calories, kilocalorie. Okay, so that's pretty easy to make the conversion to what that'll be in joules. Okay. All right, so we're good there. We've got some more basic terminology out of the way, and let's just go ahead and talk about when we look at a chemical reaction, there is a concept that involves energy. It involves looking at energy, and this concept is known as enthalpy. And I'm not going to dive real deeply into it, but I do want to cover it real quick. It's called enthalpy. Okay. Enthalpy. Okay, enthalpy can be thought of as, in a chemical sense, is kind of the energy. Okay, the energy that can be used to do work. Okay, it's energy that can be used to do work. That's enthalpy. And when we talk about the mathematics of enthalpy, enthalpy is often, the symbol for enthalpy is H. That tends to be the common symbol for enthalpy when you see it used in chemistry and thermodynamics and all that. And we'll actually be talking about thermodynamics, or I'll be linking you to a series of videos that I've already done on thermodynamics. But when we're looking at chemical reactions, what happens is the enthalpy is changing. So it's more important to, when we look at a chemical reaction, to look at the change in enthalpy, or what we call the delta H. Okay, and I guess let's just go back to how we define enthalpy. So H what it equals mathematically at least. So H equals the sum, okay, the sum of internal energy, okay, sum of the internal energy plus the product of the pressure times the volume of whatever system that we're looking at. Okay, are the different molecules we're mixing together to do a chemical reaction. So internal energy is kind of like a, I think of that as kind of, oh, I don't know, it can be, it might be in the form of heat, can be form of, chemical bonds. Chemical bonds have energy and things like that. Now, in most of the introductory chemistry that we'll be talking about, here's a really cool thing. Most of the chemical reactions that we'll be looking at, what we will assume is that the pressure and the volume of the system is going to be held constant, okay? That they're not going to change. Now, we know that this can change in real life, but to get a better feel for this, we can kind of ignore this at this point. We can hold this, and you see this when you do chemical reactions and you mix, you mix 3 milliliters of this and 3 milliliters of that, and then the chemical reaction proceeds. You don't have a significant change in pressure and volume, so we can kind of hold that constant. And so in our context, really enthalpy is the sum of the internal energy of the system that we're talking about. So really what we're talking about is the energy that's held in the chemical bonds, and is that energy released or in an exothermic reaction, or do I have to actually take energy from the environment to add to my reaction to make new chemical bonds, and that would be an endothermic reaction. So we can kind of look at the change in enthalpy as being the total amount of enthalpy I have once the chemical reaction is over. Okay, so the final. So that's the enthalpy that I have in the products. Okay, and I will subtract from that the initial enthalpy. So H initial. Okay, and this is the enthalpy in the reactants. All right, so let's just look at this here. Let me just draw an energy time. Okay, energy and time, and let's just do an exothermic reaction right here. So I have, let's say that I have 10 units of energy. Okay, 10 units of energy here. Whoop. And then my reaction proceeds, and down here I have 5 units of energy. Okay, and that makes sense, right? Exothermic. So I had a change in 5 units. Okay, that makes sense. That's cool. But here's the thing. Here's the big thing that I want you to zoom in on. What is the final in this case? Well, the final is 5 units of energy. Okay, 5 joules, whatever. And the initial is 10. What is 5 subtract 10? Well, 5 subtract 10 is negative 5 units. This is really important. So when I have an exothermic reaction, my delta H will be negative. Okay? It's negative because my final is going to be less than my initial. I am losing energy. I am giving energy off. So my enthalpy, my delta H, is negative in this case. If we contrast that, however, we contrast that with an endothermic reaction. Okay, so this is E, and time. Okay, so I'm going to start here at, all right, and I'll have my activation energy barrier, blah, blah. Okay, So I have right here, I'm going to start at 5 units, okay, 10 units. Okay, so let's write our formula up here for my change in enthalpy equals H final subtract H initial. All right, so what's my final? My final is 5 and my initial is 10. What's 5? Oops. My final is 10 and my initial is I keep messing that up, don't I? Because my initial is down here, and my final is here. So let's see here, initial, and we're going to start at, I think I totally messed this up. That's okay. So we're going to start at low energy, 5 units. We're going to go to higher energy, 10 units. Okay? So my final is going to be 10 units, and my initial is going to be 5 units. Okay? So what has happened here? Well, 10 subtract 5 is positive 5 because energy is actually being added, okay? And you have to add energy. So an endothermic reaction, the delta H is always going to be positive, or probably a better way of putting that is the delta H is going to be greater. It's going to be greater than 0. Okay, it's going to be a positive value. Okay, cool. So let's just go ahead and do a couple of equations and then we'll cut it off here. So let's do a decomposition reaction, a certain type known as a combustion reaction. What I'm going to do is I'm going to combust hydrogen gas. Again, these formulas are not balanced. These equations are not balanced yet, so don't worry about that. So H2 plus O2, and that is going to yield, okay, H2O plus heat. All right? All right, so this is what we got. H2 plus O2. This is a combustion, right? I'm basically combusting hydrogen gas, explodes. So I'm making water, and if we really want to be good about this, what we can do is we can put a little G here, and a little G here, and a little G here, and that is just talking about the physical state. G would equal gas, okay, S equals solid, and you may even here see the term AQ, which equals aqueous, or a water, an aquatic environment. Okay, so this is what we got. And then what I'm going to do is I'm going to look up, okay, I am going to look up the delta H. And looking up the delta H of this particular reaction is, for every mole of hydrogen, okay, and this is typically how we will measure these enthalpies, enthalpy of reaction, the delta H is equal to negative 286 kilojoules, 1,000 joules per mole of H2. So what does that tell me? Well, that tells me, that negative sign tells me that this is exothermic, all right, and that energy in the form of heat is released. All right, so I'm releasing a lot of energy. I would expect this to be exothermic, and that's actually a pretty large number, and we would expect that with hydrogen gas exploding and combusting, basically. Okay, so that's really what I just wanted to get at, is when you read these values, when you look these values up and of a certain reaction, it says it's a negative so many kilojoules per mole. That's really what we're getting at, is that negative is, hey, that the enthalpy of this system has decreased. Okay, my enthalpy is decreased because I'm giving off energy. Now let's contrast that to, let's say that I have somebody twisted their ankle, okay, and you're going to put an ice pack on there, and that ice pack contains two substances. Contains a little bag of ammonium nitrate, that's NH4, that's my ammonium, and then nitrate NO3. okay, and that's typically in a solid form, okay, and then it's surrounded by water, H2O, and then I pop it, okay, I pop the inner bag, and that causes the, and of course H2O is aqueous, I mean, we know that's water, and so what happens is the ammonium nitrate breaks up, it dissolves in the water, so the bonds that hold these together break up, and I have NH4 plus, which is in an aqueous environment, plus the nitrate ion, NO3, in the aqueous environment. And obviously I still have water. So what I've done is this is another kind of decomposition that has occurred, but this is not a combustion. So I've broken down the bonds that hold these together. This is known as a polyatomic ion because there are multiple atoms, and these are both ions that have come together. So I've broken this polyatomic ion down, and so what has had to happen to break that down? Well, what I'm going to do is I'm going to look up the delta H for this this particular reaction, and that delta H is 25.7 kilojoules per mole. All right, per mole. So what does that tell me? Well, this is positive, so this tells me that this reaction is endothermic, and it is actually taking energy in. Okay, energy is being taken out from the environment, and it is basically that energy is going into breaking those bonds there. And so what's going to happen is the temperature of that ice pack is going to decrease as energy is pulled out of the environment to break this ammonium nitrate down, and that's how the ice pack gets cold. Okay, so hopefully that makes sense, and you do see this a lot with reactions, these numbers, these enthalpy, these energies of reactions. So it's really helpful to know exactly what they're talking about, particularly what the positive and negative sign. You know, this is positive, so this is endothermic, negative exothermic. Okay, I think I'm going to cut it off here. Take it easy.